All right, welcome back to statistics. So today we're going to begin our journey through chapter 7. All right, now chapter 6 talked about probability distributions, excuse me, probability distributions that were discrete. So we could have an exact. Okay, you could say what's the probability that I roll exactly a 3 on a die. Continuous ones don't have that. Okay, it'll have to deal with a range. So let me explain to you why that's going to happen. All right, so I like to start this off with something called a continuous uniform. Oh, share the screen. You can't see what I'm writing. I like to start this off with something called a continuous uniform distribution. Okay, most of the things you're going to have, they're going to look like graphs. Okay, for continuous distributions, actually they're all going to look like graphs. They're going to have some kind of f of x equals, they'll give you a function, and it'll be 0 otherwise. Okay, so you're going to see something that's going to look, well, actually, I'll drag out your homework here, kind of like this. Okay, so this is a PDF, right? Probability density curve. We're going to get the GPAs of seniors here, and it's got this shape to it. Okay, it's kind of so it's got the shape to it. So it's going to look like some kind of a curve this way. And our job is to find the areas under these curves because those are the probabilities. Now, if they didn't put these on here, you would need to know what the function was, and you'd need to use calculus to get these areas. Okay, that's why I start with uniform distributions, because for the curve for the uniform, there's the curve. All right. So regardless of where we start, like say I wanted to go between 0 and 12. Okay, like maybe I know that my arrival at a bus station or a bus stop, right, I've got between 0 and 12 minutes for the bus to come. Okay, I could get there exactly when the bus gets there, or I could wait for 12 minutes, but I know that 12 minutes, like that's the end of it. It's the bus has to come between this amount. Okay, so pretend it's not in Albuquerque. All right, what we're going to do is we're going to calculate probabilities, and these probabilities are areas under these curves. Okay, so like the probability that say x is less than or equal to 6, right, that would be halfway. So let's go ahead and shade that in. All right, so here's 6, here's my value. And what I'm looking for is what is that area. Okay, my y value here is 1/12. How did I know that? Well, I know that the whole area here has to be 1. So if I've got a rectangle, I know the area has to be 1, and I know the length has to be 12. The length is 12 because that's what we set up. What's the height? Right? So we know length times height is equal to 1 because the whole probability has to be 1. That's a rule. Okay, and I know that my length happens to be 12. 12 times h equals 1. H has to be 1/12. Okay, so if I get this area here, if I want probability x is less than 6, well, wouldn't we just have to figure out like what's the area of this little rectangle here? So that's going to be, well, what's my length? My length is 6. My height is equal to 1/12. So length times height is equal to 6/12, which is equal to 1/2, which is exactly what you expect when I said, well, what if I wait half the time? Well, the probability that the bus occurred between 0 and half the time is half the probability. So it's a 50% chance the bus comes between 0 and 6 minutes. All right. So all we're doing here is we're just calculating the areas of rectangles. Now, the whole rectangle has to be area of 1, but part of that rectangle is going to have less than 1 as an area. Okay. So if I wanted to figure out like what's the probability that say x is between 2 and 6. Okay, so we're just going to draw the picture. We're going to say, well, here's my, we're always doing the same rectangle here. Okay, so here's my curve, 1/12. Okay, so multiplies out to 1. So we want between 1, 2, and 6. All right. And we're going to say, well, what's the area of this little piece in here? Okay, what's the area between 2 and 6? All right. So what we're going to do is we're going to say, well, what's the length? The length is equal to 6 minus 2. The height is always 1/12. Okay, for this particular scenario, the height's always this. Okay, so 6 minus 2 is 4. Okay, 4 times 1/12, we end up with 4/12. I think we can cast out a 4 here, and we get a probability of 1/3. This is my probability. All right. The reason why we can't have exact, okay, is what's the probability that, say, x equals 6, as opposed to x is less than 6. Okay, so that's a different answer. This is not the same probability that x is less than 6, probability that x is greater than 6. It's not, these are not the same things. I have a lot of students say, well, it's 1/12. Like, I didn't ask you for the probability that x was between 5 and 6. That would be 1/12, because the length is 1 and the height is 1/12. So it's 1 times 1/12. Nor did I ask you for, like, between 5.5 and 6.5. This would also be 1/12. So some people get a little bit better. Like, well, what about 5.9 and 6.1? Well, 5.9 and 6.1, right? This would be 0.2 over 12. Okay, it's not the same thing, right? This is different than probability that x equals 6. It's close, but it's not the same. Probability, how about 5.99? You see where this is going? Like, this is still not the same, right? This is 0.02 divided by 12. Okay, there's 2 pennies between something costs $5.99, something costs $6.01, right? There's 2 pennies between them. So 0.02 divided by 12. Okay. Anybody who's looking at this thinking, you shouldn't have decimals and fractions in the same statement. You're right. This bothers me to look at it, but we're not trying to do a calculation. We're just trying to demonstrate a point here. Okay. No matter how close I get, it's not going to be quite the same, is it? And this is going to get smaller and smaller and smaller and smaller. So the probability that x equals 6, right, that's equal to 0, because we don't single out like one specific spot. Okay, philosophically, you think like, what's the probability that a human being is 5 foot 9 inches? Exactly. Not one hair above, not one hair below. So how many decimal points do you have to go out for this to happen? Like, lots, infinites. And our restriction to the modern world, yes, everything is discrete, but meaning that atoms make everything up, everything is quantized, but it's never going to happen where you can get exactly that amount. It's always going to be a tiny little bit of range in between them. Okay, even to like where one of the electrons is dancing between orbitals, like, it's never going to be exact. All right. So the probability that something exactly equals a number in continuous is 0. All right. You could also go back, and I'm sure you remember your high school geometry classes perfectly. But one of the first things you learn in high school geometry class is that the width of a line, right, that width is 0. If you've had the pleasure of taking calculus, what you're doing is we're getting area under a curve. So as soon as I said that, everybody in calculus is now having horrible flashbacks. But what we're doing, okay, this is a calculus symbol. It effectively means the sum. Okay, but what we're doing is we're taking our sum, our integral, from like a to a. What happens is we're going to get f of a minus f of a is always going to be 0. Okay, so if you haven't taken calculus yet, don't worry about this. This isn't coming up Okay, every once in a while I'll bring it something like this up, but it's not. If you're calculus illiterate, it's fine. We're not testing you on this. Okay. So probability that x equals 0, probability that x equals a number, that's 0. Okay. In continuous distributions. Okay. If it's a discrete distribution, like what's the probability that I roll a 3 on a die? It's 1/6. Okay, even though it says exactly, I roll exactly a 3 on the die, it's still 1/6 because there isn't like a 3.1 or 3.2 I can roll or a pi I could roll. Okay, it's 3. That's the die roll. So that's what you're stuck with. Okay, so for discrete distributions, like all the 6.1 stuff, if we say exact, I'm expecting a non-zero, well, it might be 0, but generally you're going to calculate something out, right? You're going to get your binomial distribution, or you're going to look at that table, or you're going to like calculate it out because it's a die roll, something like that. That to be exact. But if it's continuous, we say, what's the probability that this exactly equals that? That's 0. Okay, because we're always trying to compute an area with our probabilities. Okay, so that's all we're doing is we're just calculating areas. Easier said than done, but we are calculating an area. All right. So a lot of times, I apologize for this, I will go back and forth between saying computing a probability and computing an area because they are the same thing. Okay. So when I look at this curve here and they say, wow, we have a probability density function of GPAs of graduating seniors, we should all be so lucky. Okay. Find the proportion of seniors whose GPA is between 3.6 and 3.8. But what area is between 3.6 and 3.8? And that would be 0.23. Okay, that's what they want. The proportion of seniors, the probability that they're going to be here, the area under the curve between 3.6, 3.8, it's all the same. Okay, what's the probability that they're going to have greater than a 3.8? Well, they didn't tell us. Okay, we got to actually calculate this out. So the areas have to sum up to 1. All right, just like in the other one. Okay, all probabilities, they have to sum out to 1. So these areas, 0.67 plus 0.23 plus, I don't know, this has to be 1. All right, so I think we could do something like this is 67 and 23. This is going to be 6, 7, 8, 9. This is going to be 0.90 here, 0.90 plus I don't know equals 1. Right? If something costs 90 cents, right? What change for $1 do you make for 90 cents? We have 0.10 left over. Okay. So if we could scratch this in here, I would say 0.10. Okay, that would be right here. So the probability that GPA is bigger than 3.8 is 0.10. Okay, we don't for this trailing 0, but everybody else has 2 decimal places. I'm just going to make it consistent. All right, great. So we're going to move on to a specific distribution. Okay, not. I wish it was. I wish we could do uniform. I like rectangles; they're easy. Okay, but we're going to do something called the normal distribution. If you're going into electrical engineering, maybe mechanical engineering, they often call this thing a Gaussian because that's who came up with our curve here. But that's the name of it is called normal distribution. Okay, lots of things in math are called normal. I don't know why. But the function that we have for this, okay, and I think it's important. I think it's important for you to see it once. Okay, so our f of x is equal to, this is e, well, it's 1 over the square root of 2 pi theta, or 2 pi sigma rather, squared. E, and this is all in an exponent. Negative x minus mu divided by 2 sigma squared. No, 2 sigma squared. Okay. So that's what our formula is. And now we are going to have to figure out areas underneath this thing. So let me explain a couple of things to us. Okay. You've met pi before, right? Probably in a geometry class, but you know this is the ratio between the what is it, the radius? No, the circumference, and yeah, the circumference and the radius. Okay. But you know, 3.1415 dot 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 dot. Okay, you've met this one before. Okay. Sigma, this is a standard deviation. Okay, we could calculate this. This will often be given to us. Okay, but this is a standard deviation. X, this is the value of what we're looking for. Okay. Okay, now I said the area underneath the curve is going to be 0, but what this curve looks like, you know, we talked about bell-shaped curves in the middle, beginning of the class. This is the height, right? If I pick this particular X, what it's going to do, it's going to tell us what height that is. Okay, if we plug it into this formula. So if we want to plug it into this one, we're going to get this height, but the area under the curve here, okay, is 0. So we would need between x equals A, x equals B. We would calculate these things and then figure out what this area is. Okay, so, but wait, you said we need a calculus for this. We do if we want to do it by hand. Actually, calculus can't do this because this is a function that if you are in calculus, you can't do this. Okay, so you can't do e to the negative x squared over 2. Can't do it. All right. Pick any A and B you want. You can't do it. Well, A equals B you could do. Everything else you can't do. So even the people who've taken Calc 3, like, you can't do this. All right. You don't. This is not a thing that's taught in undergraduate classes. To do this by hand. We have tables. Okay. We have calculators. That's how we're going to get these numbers. So for the people who have not done the calculus yet, this is a calculator exercise. Okay, the calculator has these areas that can compute them very quickly. We're going to use the calculator to get this. So don't be intimidated by this. It's just what we're doing. Okay. Mu, right? So this is sigma, remember. This is mu. This is our average, right? This is our mean. Okay, so we have that. Okay, so the only symbol on here right now, because we could check off, right? We can say, well, okay, you know, X isn't so bad. I don't like it, but it's not so bad. Average, we've seen that before. We can deal with it. Never really understood standard deviation, but we've calculated one, so that's okay. Same thing here. Pi, you may never have liked pi, but you've at least met pi before. So what the heck is this? What's E? It's not the E on your, well, it is an E on your calculator, but it's not the one you're thinking of. Okay. E, okay, E is a number. It's like pi, okay? So it's approximately 2.718281828, and then 5. Okay, and then it keeps going. It just keeps going. It's kind of like pi. It's around 3, right? Pi is close to 3. E is close to 3. Okay, and they're the same kind of number where they don't. You say, what about this 1.28? And yeah, it happens twice, and then it does other things. So that doesn't repeat reliably. Okay, it doesn't repeat in any sort of a pattern. It just goes on and does its own thing after this. Okay. The reason I will know this thing, the reason I know this thing out to about 10 digits. So I'm sorry, I'm going to burden you with this piece of trivia, but the person who taught me this back in the 80s was a huge Andrew Jackson fan. Like, that was his thing for American history. He loved Andrew Jackson. This was back in the 80s, so it doesn't quite have the same connotation as it does today, which is beautiful because I'm introducing this on Indigenous Peoples Day. Andrew Jackson is responsible for Trail of Tears, so forgive me for that. But that this was the year he was is inaugurated. So if anybody ever asks you, like, when was Andrew Jackson inaugurated? Hey, that's part of E. That's 1828. Okay, you'll impress all of your friends. Okay, trivia night. All right. The other way to get E, this is the way I usually think about it, is you guys remember what a factorial is, right? Like 5 factorial. This was 5 times 4 times 3 times 2 times 1. 0 factorial was 1, right? Because it's how many ways can you arrange no items? We define that as 1. Say, I've got nothing. Here's my arrangement. We're done. Okay. This was 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, plus you see where this is going. Okay, but that's another way to represent E. Okay, so someday I'll rebrand this video as a Sesame Street one that's brought to you by the numbers I and E. You'll be all set. Right? So that's what E is. Okay, it's a number. It's like pi. But we're not going to be responsible for calculating anything out of this formula. Okay, so this is not something you have to memorize. I would prefer that you didn't. But one of the things I think you should learn in a college-level math class is that there are numbers, right? There's numbers called E. There's a number called I. So that's where we're going with that. All right. So, right, calculating some things. So let's do a little bit more of your homework here. Show you how to do this. Because even the homework says, hey, we're going to calculate this shaded thing using this calculator. Okay. They say T84, but T83 will work just fine. Okay. So we want the shaded region. Okay. So I wish they would have given me a slightly easier problem to start with. All right. It's not that this is going to be a hard thing to do. It's just that this is a more than problem, right? We have 0.86 here. That's my z-score. You remember z-scores from the beginning of the class where we did x minus mu divided by sigma. Okay. We use a standard normal graph. That means the variable is z instead of x. Okay. And we want this area up here. Okay. So the z value is 0.86, 83, sorry. 83. So what I want to do first, okay, is I'm going to calculate the area, okay, to 0.8, up to this value. So I'm going to do this. This is what the calculator is going to tell us. Okay, is this area? What does the pink area and the purple area, what do they have to add up to? These areas have to add up to 1. So once I know the pink area, how am I going to get the purple area? I'm going to say 1 minus whatever the pink area is. All right, is going to be the answer I'm looking for. All right, so let's go to the calculator, and we'll show you how to type this thing in. We're gonna do this a lot. Okay, this is your life, like the next 7.1, 7.2, 7.3. Okay, so this is a skill that you're going to need to have, but we're going to have a lot of time to work on it. Okay, so what we're going to do is we're going to do second function distributions. Okay, and you see where it says normal PDF, normal CDF, inverse norm. Like these are the 3 that are the important ones. Okay, T is also an important one, so that's why it's second. Okay, so what we're going to do is we're going to go to CDF. Okay, I don't remember this one. So I think we're going to say we have a mean of 0. We have a standard deviation of 1. When you have a standard normal, for a second here, easier to see. When we have standard normal, okay, the mean is always 0 and the standard deviation is always 1. Okay, when we get to 7.2, we're going to do non-standard normals. So we're going to have to convert them to this. And the way we're going to do that is by z. All right. So we're always going to be converting the standard normal. I'm lying a little bit here, but bear with me. But for standard normal, this is the parameters you're going to have. Okay. And we want to, I think the next one is x, 0.83. And we'll type that in and hope that is not correct. Oh, I don't know it's not correct because look, this is not point. This from 0 up to 0.83 is not 1/3 of the data of the values. Okay, it's just not. So let's see. Hold on, I'm gonna pause and check. All right, there we go. All right. So bring up your second function. I got it now. Normal CDF. All right. Now we need to put in a lower amount, the upper amount, and then the mean and standard deviation. Okay, let me write that down. Okay. So it's norm CDF, low, high, mean, standard deviation. All right. Now, when I need a low or high amount, okay, this curve extends off to negative infinity. And this curve extends off to positive infinity. Okay. The area is still 1, right? Even though it goes further and further and further out. It's just these get really, really, really tiny and you can't add them up. Okay. So when I say low, understand it's low relative to that mean. Okay. Your book is going to suggest that you put in -1, this e to the 99, okay, which is -1 bigger than our national debt kind of exponents. Okay. This is -1 with 99 zeros after it. And the way you would do that, okay, and this is you have to be careful because it's not the way you think it's going to be. Okay, it's -1. And you see this little EE, this yellow EE here above the comma? That's the one you have to deal with. Okay, that's the -1 e to the 99. Okay, it's not alphabet and go to E here. That's not going to do it. Okay, your calculator is not going to understand what that means. You need to use this EE button right here. Okay, but it's just relative to that. If you don't want to type all of that in, like, let me put it this way: for standard normal, negative, what was the area? What was the amount of probability? What percentage was between -3 and +3? That was 99.7, right? So -3 is a pretty low number for a standard normal. So if you go out to -10, -100, that's a low number. You don't have to be this extreme. Okay, I'm just going to use -100. All right, we'll get the same answer to as many decimal places you can see on this calculator. All right, so we're not going to worry about that so much. At least I'm not. Okay, but it's low relative to the mean. If we have to go to a higher number, it's going to be high relative to a mean. Okay, and again, for a standard normal, mean is 0. 3 was a big number. So if I go out to 100, that's huge. Okay, so what we're going to do, okay, is we're going to do standard normal. Okay, so we're going to go distributions, normal, CDF. Standard normal just means that the values are going to be 0 and 1. So we're going to say 0.83, comma. What's a high number? Well, you could type in 1 EE to the 99. That's a really, it's like one of the biggest numbers you can have on your calculator. Okay, it's a really big number compared to the mean 0.83. Okay, that's just going to tell us what this value is right here. It's going to take this area because we started from the low here and we're going all the way up. Okay, and then mean and standard deviation. Okay, enter, and then there we are. So 0.2033, 0.20326, but the 6 is going to make that a 7. So 0.2033. All right, that's our answer for that one. So 0.2033 to 4 decimal places. If you ever have a doubt, it's always 4 decimal places. Okay. So this one, okay, this was negative 2.13. So I want this area down here. Okay. And again, here's our average. Average is 0. Standard deviation is 1. Right. So we're going to go to normal distribution here. So second function, there's normal CDF. Okay. This is going to do, we need the lower number here. Okay, so pick a small number relative to negative 2.13. Okay, so what if I pick negative 1 EE to the 99 up to negative 2.13 with my mean of 0 and my standard deviation of 1. 0.01658. So 0.01658. But since this is an 8, we're going to say this is 0.0166. Okay, to 4 decimal places. 0.01699. I'm going to calculate this a slightly different way. Instead of going all the way down, that's a lot to type in. Negative 1E99. What if we just type in negative 100? Okay. So what if I type in negative? So you look at this number. We'll have it still up here. So it's second function distribution, CDF. All right, and we're going to say negative 100 up to negative 2.13. All right, and then we have our 0 and 1. Look at that, like 1, 6, 5, 8, 5, 7, 4, 7. It's the same number. Okay, so whatever makes you happier to type in, type that one in. Okay, if you like you read the book and you're like, they use negative 1E99, be my guest. I would prefer to use a smaller, not as much key presses. Okay. So there's my value here, 0.0166. So not 166. Okay. Number 3. We want the area between 0.35 and 0.76. This used to be a really hard problem because we'd have to look these numbers up on tables. Not anymore. So we do second function distribution, CDF, go down to 2. Okay. Now, the low number here is 0.35, and the upper number is 0.76. All right. So we don't need to go like all the way off to infinity and beyond here. We just go between these two numbers. All right. It's still the same idea. We have 0 and 1. All right. And that's how we're going to calculate this. Okay. So 13954. 13954. 13954. So 4 decimal places, this 4 doesn't contribute to the 5 there, so this is 0.1395. Okay, that's almost 14%. Okay, so this is 0.1395. Okay. It looks a little small to me, so I'm double checking my problem here. It looks okay. All right, well, there we go. So yeah, that's and we type those in. Let's check. Oh, we still have more. Oh, look at this. Let's see. Finally, we got one that's good. All right, this one. There's 2 ways to do this problem. I would prefer that you did it the easier way. Okay. So what area? We have negative 0.55. So we're going to go here, negative 0.55. And then here, we're going to go 0.75. Okay, here's 0. What we want is a shaded region here is this and that. All right. What if the green this time, this green. What do all the shades have to add up to, right? The blue and the green, what does it have to add up to? It has to add up to 1. So why don't we take 1 minus whatever the shaded area for green is? What are you going to be left with? We're going to be left with that blue area, okay? So rather than come up with 2 problems, we have to do a normal CDF for this part and then this part and then add them up. Why don't we just do normal CDF for the center part and subtract it from 1? Okay, so let's go ahead. We'll do this in 2 steps here. So second function, distributions, normal CDF. Okay, we're going to go from negative 0.55, that's my low number, to 0.75, that's my high number. We are still working with a standard normal, so we have a 0 for a mean, standard deviation for a 1. Okay, so that was 0.4822. So this guy here, 0.4822. Okay, that's what this area is. So what I'm going to do is I'm going to say, if we take 1 minus 0.4822, right, we should get 5178. Okay, so 1 minus 0.4822, 5178. The way I do this, to do my you don't have to do it this way because you have a calculator in front of you. A lot of people are happier with that. Like, okay. I used to be a cashier. Like when I was going to school, I worked at Conoco and worked a night shift. And people would come in and they'd buy gas. And usually they, it depends on who they were. Sometimes they buy a lot of gas, sometimes they wouldn't buy some gas. But invariably, these people would ask me, here, I bought $48.22 worth of gas. Here's 100. Okay. So I got really good at being able to make change for, like, if you bought $48.22, like I could make change for 100. Okay. And sometimes the cash register worked and sometimes it didn't. So what I mean by that is sometimes you had to make the change yourself. So I'm just used to, like, well, I've done this a lot. I just move, because I can't do 0.4822. Who does that? But can you make change for $48.22 from 100? Yeah, we could do that. If you've been a cashier at all, maybe not so much because people use debit cards more than they use cash these days. But somebody stopping gas in the middle of the night in a truck, maybe they're being legit and maybe they're not. So they pay in cash. All right. So that's where we have that. Okay. So this was 0.5877, 5178, 0.5178. Okay, so it's not magic. It's not even, it's practice, but it's not even practice. That would have been like, you practice as a math teacher. I'm like, no, I practiced as a cashier. Okay. So there we go. And the way to get good at that, by the way, is to actually practice. Okay. So if you are used to going to a grocery store and picking up your groceries, like, do you know how much the bill is going to be when you get to the register? If you have to work within a budget, you do. Okay. So even if you don't work, even if you can't do it yet, that would be useful. Start practicing. Okay. See how close you can get. Make a game out of it. If you have to bring your kid to the grocery store, make them play with you too. Okay. Your mental arithmetic will go up. Okay. You'll be better for it. I'm probably going to stop our video here so that we can start another one and concentrate more on some problems here, because I think this one's been long enough. So we'll do some more in a minute. Okay, I'll be right back and we'll play with that. All right, good luck. See you in the next video.